Hello, today we are going to work on a steam compressor as a steady flow device under the category of open systems. So let me review the information. The information given are the quality of steam at the inlet is 95%. Pressure at the inlet is 750 kilopascals. So the compressor receives shaft work in the amount of 180 kilowatts, and there is a heat loss of 50 kilowatts. So I'm gonna show this on the diagram. This is our Q dot loss. The exit conditions are 3 megapascal pressure. That's the only exit condition that we are given at 0.2, and the mass flow rate of steam through the system is 6 kilograms per second. Let's try to solve this. So we always start by writing the first law of thermodynamics for an open system steady device, which is Q dot in plus W dot in plus sigma for all inlets, M dot times H plus kinetic energy plus potential energy at inlet must be equal to Q dot out plus W dot out plus all outlets energy transfer by mass, which is M dot times H plus V squared over 2 plus GZ. Now we need to simplify this for our problem. The compressor doesn't have any heat added to it, so there's no Q dot in. It is a compressor, so we do have work in. The compressor has one inlet, one outlet, so we don't need the sigma sign anymore. So is at the outlet, no sigma sign. There's one inlet, one outlet. Then let's get to the terms on the right-hand side. It is a compressor, so it does not generate any type of work. So this is 0, but in this case, we do have some heat loss. So we'll keep this term here. Now let's get to the assumptions for kinetic energy and potential energy. No information is given as to whether the inlet pipe diameter and exit pipe diameters are different. So we assume that they're the same or approximately the same, which means that there is no significant change in kinetic energy between inlet and outlet. We can scratch these two terms. Again, usually for compressors, the elevation difference between inlet and outlet is not significant, so we can scratch the potential energy terms from the equation. Now we can write the simplified form, which is just W dot in plus M dot in H at inlet equals Q dot out plus M dot out H out. Now, instead of in and out, I'm going to use 1 and 2 just for simplicity. So this will be M dot 1 H1 equals Q dot out plus M dot 2 H2. I kept in and out for work because we don't have work at position 1, position 2. Work and heat are transitive energies and only are only defined when they cross the boundaries. So this is the form of the equation that we will work with. We know that W dot N is given. Here we need to determine H1. So H1, let's review the information that we have for H1. We have X1, which is the quality of the steam, as 95%, and P1 as 750 kilopascal. This means that the phase is saturated mixture because the quality is given. So we need to use the formula for H for the saturated mixture, which is HF at the given condition plus X1 HFG. Now we can read those values from the table for saturated steam. HF at 750 kilopascal is 709.24 plus quality of 0.95 times HFG at 750 kilopascal is 2056.4. And the answer for H1 is 2662.82, and the unit is kilojoules per kilogram. So we determined H1, which is an important step. W dot N given, M dot 1 given, H1, we know it now. Q dot out is given, M dot 2. We notice that mass conservation tells us that M dot 1 and M dot 2 are the same because it's a steady flow device. Now we can plug in into this equation. W dot N, 180 kilowatts, which is the correct incorrect units, plus M dot 1 or M dot 2, both are 6 kilograms per second, multiplied by H1, 2662.82, equals Q dot out is 50 kilowatts plus M dot 2, which is 6 times the unknown H2. We want to solve for H2. So our H2 is going to be 180 plus 15,976.92 minus 50, all divided by 6. And therefore, our final enthalpy is equal to 2954.5 kilojoules per kilogram. So there's one more step left after determining H2. Now we need to go back to tables and determine the phase and then read the temperature value. So the information at the exit is H2 is 2954.5 and P2 is given as 3 megapascals. So usually what we do is we need to go to the saturation table. So in the saturation table, see if our H2 is between HF and HG at 3 megapascals. We'll see that this is not true, meaning that it is superheated because the H2 is larger than Hg at 3 megapascal. Now we need to go to the superheated table under 3 megapascal and look for H2, which is 2954.4. We'll find out that T2 is between 250 degrees C and 300 degrees C. We need to perform interpolation, and the result will be T2 equals to 285.5 degrees C, and this is our final answer.